Okay, this is question 2.114. Use the energy method to find the natural frequency of the system. Okay, so the figure is given down here. It's a cylinder restrained by springs. So the first step will be to find the kinetic energy or the potential energy. I'm going to find the kinetic energy first. So find the kinetic energy first. So what is the kinetic energy of the system? Kinetic energy only consists of masses. Okay, anything that moves. Okay, so basically it needs to have a mass because the formula for kinetic energy is half mv squared. So there's two here, it's m and also g naught. All right, so it means the mass, the cylinder mass here is moving in two kinds of motion, translational and rotational. In terms of rotational, it moves counterclockwise. So when it moves counterclockwise, so the whole block of cylinder is moving to the left. Okay, theoretically speaking. So from that, there are two kinetic energy, which is one is for the translational, half mx dot square, plus one is rotational, half g naught theta dot square. Okay, so from here you can choose either to solve everything in terms of theta or everything in terms of r, but for this question I would prefer to settle for theta. Okay, for next question only then we can try settle using x. So now we try to settle for theta. So try and substitute whatever that is possible to substitute. So you know that x equals to r theta, right? For this block, the r is the r lah, the r theta. Okay, the radius is the r, the big R. So if I want to substitute x dot, so I'll substitute r theta dot. Okay, and then settle for x and theta, and then I want to make everything in terms of m. I don't want m and j in one formula. Actually can, but depends on you. If you want to solve everything in terms of m, better that way. So if you follow the formula in lecture 4 slide, for cylinder, right, for circular cylinder mass, the formula for j is half mr squared. So you can substitute j to be half mr squared. Okay, so now I've taken out everything that I want to substitute. So just substitute everything inside here. So x dot will be r squared theta dot squared. J naught will be half mr squared theta dot square. Settle if you can settle. One over 4 mr squared theta dot squared. Since both of these are the same basically, so you can solve it further to be 3 half plus 1 quarter, you get 3/4, right? mr squared theta dot squared. Okay, then from here I can find the differentiation, because we want to do energy method, you have to differentiate the t and differentiate the u, right? So differentiate the t in terms of theta. So the squared for theta, bring it to the front, times 3 over 4. 3 over 4 times with 2, you get 3 over 2 mr squared. And then theta dot, the squared minus with 1 already becomes theta dot to the power of 1. And then chain rule for differentiation, you have to differentiate the theta itself. So theta dot differentiate, you get theta double dot. So that's the differentiated formula for t. Okay. Potential energy. So for potential energy here, I'm going to do it up here. So potential energy, which is the U, okay, the U here, potential energy for this part is only for the K. Okay, potential energy is only for the K. So the potential energy will be half kx square, right? And for k1 is half k1 x1 square. For k2, half k2 x2 square. But now the x in this formula is the displacement, all right, for the springs. So the displacement that happens for the spring is, as you can see here, both k1 and k2 is situated at the same point on the cylinder block, which is the distance from that point to the center of the cylinder is A. Okay, and the radius of the cylinder is R. So the total length from that point to the ground is A R plus A, right? So when the block moves to the left, this point here, for example, let's say for K2, this K2 here will expand to the left, all right, following the block, all right. As the block moves to the left, the K2 also will expand to the left. From the point to the end of the block is the distance of the displacement, which is R plus A. Okay, and since K1 and K2 is situated at the same point of the circle of the cylinder, so K1 and K2 will experience the same displacement. So now we know that x equals to r theta, and our r for springs is r plus a theta. Okay, so here now you can substitute all the values. Remember the displacements for K1 and K2 are the same, so U half K1 our x1 now is r plus a squared theta squared plus half K2, the displacement also the same, r plus a squared theta also squared, because you substitute inside x, right? X is squared, and then I'm going to factor out whatever's the same, all the same stuff in this equation. So I'm going to substitute, I'm going to factor out half. Okay, I'm going to factor out r plus a squared. I'm going to factor out theta squared. Okay, and then I'll be left with K1 plus K2. This is what happens when I've already factored out all the same parts of the equation. Now I'm going to differentiate following the energy method. Differentiate U with respect to T. So I'm going to differentiate the theta now, right? I'm going to differentiate the theta. So the square, bring it to the front. If we differentiate theta, so the power for theta multiply to the front. So half times 2 equals to 1. We'll be left with r plus a squared theta, and then differentiate again the theta. For chain rule, you'll get theta dot K1 plus K2. Okay, or I'm just gonna bring theta to the front, easier that way. Bring the K1 and K2 to the front, theta to the back. Okay, done. Now I've already have the differentiation of dt and also the differentiation of du. So the third step would be find the energy method, which d over, this is the energy method, and d over dt, t plus u equals to 0. So now I'm going to bring this thing here plus both of these differentiated equation for t and u, add them together, equate them to 0. Okay, now you have to solve this and make this into an energy EOM, all right, equation of motion. So in order for us to do that, let's try and simplify this. What can you solve for this one, for this line here? You can solve for theta dot. Okay, since all have theta dot and on the right side is equal to 0, so you can divide the whole equation with theta dot to cancel all of them together and to get rid of theta dot. So you will be left with 3 over 2 mr squared theta double dot plus k1 plus k2 times r plus a squared theta equals to 0. Okay, then since I want to make this into an energy equation of motion, the equation of motion will be theta double dot plus omega n square theta equals to 0, right? This is the equation of motion. Okay, this is equation of motion. So I'm going to make it into equation of motion. So what I have to do is make theta double dot alone. So since now our theta double dot is not alone, so I have to divide the whole equation with 3 over 2 mr squared. So now divides the whole equation with 3 over 2 mr squared. So I'll get theta double dot plus k1 plus k2 times r plus a squared theta over 2 mr squared equals to 0. Okay, and since our equation here that if theta double dot is already alone, then this is an EOM. Besides theta is omega n squared, right? So this over here, besides the theta, is omega n squared. So our omega n will be square root of this thing here. And that will be the answer. Okay, as simple as that. This is your answer for omega n using that you get from using energy method. Okay, and these are all the steps that you need to know. Alright, and that is how you settle for question 2.114.